Hello, Gabriel.
Hey,
Hey, how are you?
I'm good. How are you?
Good. I'm Weston. Nice to meet you. I'm
Nice to meet
helping to
you as well.
organize. I know you've sort of been bouncing between discussing with SR and Angel and myself.
Okay. Well, it's nice to finally meet you.
Yeah, you do. Sounds like an interesting seminar. Before we get into anything, is there anything you want to test out technology-wise? Right. So today we're pleased to have Gabriel Patrón with us. He's a statistics major from the Universidad Nacional de Colombia, and he's going to be presenting to us on generative models today. And he says that his interest in these came from a variety of different applications, including Markovian composition of music, and currently he's applying his skills to working at a financial tech startup that performs risk capital calculations while also getting a micromasters from MIT Finance. So he's going to talk to us about the use of these models and how they may apply to climate science. So we're very excited to have him here with us. And Gabriel, I'll let you take it away.
Okay. Thanks, Weston. Thanks everyone for being here. I'm really excited to be presenting to you a topic that is for me one of the most interesting things going on right now. So let's just get started. Well, this work, at least a longer part of this work, just came for me as a thesis in my undergraduate statistics studies at the Universidad Nacional de Colombia. And if anyone ever gets curious and wants to get to know the whole thing, I can show them. Just hit me up. Oh, I'm just gonna start with some motivation as to why this is so cool. You see these images from left to right: a dog, a landscape, a butterfly, and a burger. And I think it fools me even if I told you, but I can tell you that all of these are fake images. That none of these images are actually real. They are generated by a neural network. Uh, and in fact, they are generated by the same neural network. So this is a big thing. Imagine if you could just produce any kind of image you wanted on demand, like realistically, and that fools like anyone, uh, uh, any single casual observer. So I think that's really cool. I'm gonna show you, and if this were other place, I'd ask you if you thought these people look real to you, but I think you already know the answer. And all these people I'm showing you are actually samples from a special kind of GAN, and GAN is actually the model I'm here to talk to you guys about. Mm, the well, I mean, so far we've seen faces, we've seen a dog, we've seen everything, and you might wonder, like, how could you use a neural network that knows how to very appropriately generate samples from a distribution? And I would answer you that there are actually some useful things that GANs have been doing so far. For example, medical data augmentation. We can show that if we augment our images with synthetic images, sometimes the accuracy of classifiers improves, and that's a very big deal for medical science. And not only in medical science, but actually business has been undergoing a revolution, specifically fashion business, because now we can also generate uh, basically everything that comes from a photo shoot. Let's say we got a model and we just, or we got some clothing articles that we just want to showcase, and we just add a heat map and the articles, and then we can almost generate a model from our generator. And we can also generate basically anything we have images on. And I have made like a very short emphasis on images, but these kinds of models actually work on almost any kind of data you might come up with. So I'm gonna start talking here about about generative adversarial networks, which is the architecture that is used to generate everything I showed you guys before, and how it's used. What's the framework here that we're in the middle of, and how it was and has been improving with time to become to solve some of the issues of the initial formulations for GANs. So let's get started now, right? I think we should get started with talking about generative models, and these are just defined as a group, as a class of algorithms that ideally learn how to model data, that learn how to uh, establish properties and parameters, and just um, copy, distributions of data that we come up with in everyday life and any research applications that we might think of. We are inside this framework. We have some data and we want to learn its distribution to study not only its properties, but we also want to generate samples from it. This is the basic generative modeling framework. And generative adversarial networks fall under this umbrella of generative models. These generative adversarial networks have just been showing some amazing results, and people are really excited about them and everything they have been able to do and what they're gonna be able to do in the future. So this is what we are gonna do. We're just gonna make two neural networks clash with each other, compete with each other. We're gonna have the first neural network called the generator, which tries to output fake data that ideally will fool the second neural network called the discriminator. The discriminator on its own is trying to classify real data as real and fake data as fake. Mathematically, we're gonna define all this way. We have the initial data distribution, and we're gonna have a latent dimension. We also have the generator, which is gonna map from the latent dimension to X, X being the domain of our data, the theoretical domain of our data, with we surely don't know. And the discriminator is going to output some mapping from X to the interval 0 to 1, namely probability on this image or this sample being real or fake. In this case, G and D compete. And ideally, the distribution induced by G converges to the distribution of the original data in the limit. This becomes a non-cooperative Nash game uh, represented by this equation, in which the generator is going to try to minimize this expression, and the discriminator is going to try to maximize this expression. It makes a lot of sense if you take a while and just study it. The term in the left is just the discriminator trying to classify real data as real, and the right term is the generator trying to minimize the samples the discriminator just classifies as fake, and the discriminator is just kind of not letting itself be fooled by the generator. In reality, we use the second expression in the footnote because it provides more of numerical stability to the convergence of the distributions in the limit. Ideally, this is like in what we're working with. let's say we have like our original distribution, which here is represented by the distribution in the black dots, the generated distribution, which is represented by the green line, and the discriminator, which is represented by the blue dotted line. In this case, uh, the progression tends to be that the generated distribution learns how to simulate the original distribution and to generate samples that plausibly come from the original data distribution. This is like another way to see it is just uh, these blocks of iterations in the algorithm in which we sample uh, from the latent distribution and transform it to generate fake data. We sample from the real distribution and make the calculation and just ascend its gradients through the for the discriminator, and then we update the generator, and then we again update the generator, and then we update the discriminator, and we go on and on and on, and ideally it becomes a positive feedback loop that in which the generator and the discriminator, through their mutual feedback, actually improve each other, and thus the generator starts providing uh, like realer and realer samples each time, and the generator becomes better and better at distinguishing between generated data and fake data, and generated data and real data. Uh, so this is like a diagram that works a lot for me. We have like the images provided by the generator. We have real images that come from our original database, and we pass them both to the discriminator. And the discriminator classifies them as real or fake. And then with that, we calculate our cost function that we then use to just, through its gradient, update the weights on the discriminator and the generator. We have, but in its initial formulation, mostly, we have many problems, just training GANs. Mostly the non-convergence issue and the stability issues. Sometimes the GAN, mostly the generator, gets stuck on somewhere, and it doesn't provide like any meaningful images. And even when it's converging, sometimes it seems as if it's going to converge, and then we kind of lose all the progress suddenly because the network just gets out of control. So I'm just going to name a few of the problems and just add some empirical recommendations and explain why these things come up. So we have these things. We have a hard to achieve Nash equilibrium because we are in a two-player non-cooperative game. So in this case, even if the function is a convex function, the stability is hard to find. We also suffer from low support manifolds and vanishing gradients. This is going to be very important because uh, the low support manifolds is going to have some mathematical implications that we're going to study later on. And the vanishing gradients, well, if we have like zero gradients, then that would explain why our generator gets stuck, because it has no gradients to update its weight. We also are going to suffer from mode collapse and a lack of proper evaluation metric. And I'm going to start showing you guys what I mean by all this. When we have like low dimensional support, it means that in high dimensional spaces, support of real distributions and generated distributions are often disjoint, such as the image on the left. And or negligible as in the image on the right. And this is going to have some very important consequences on the way we measure distance between distributions and the effect it's going to have on actually the convergence of probability distributions in high dimensional spaces. Vanishing gradients are also a big issue here. Almost zero gradients are obtained via regular GAN. As we can see, the original GAN discriminator, as pictured here in the with the red line, provides almost zero gradients almost everywhere, and that's going to have some issues because we are not going to be able to update our neural networks to keep them improving more and more. There's also the issue of mode collapse, and the generator does not need to generalize to fool the discriminator, actually. If we measure the generator's success as the rate at which it fools the discriminator into thinking that generated images are real, actually, it only needs to learn how to reproduce a small subset of the data and just forget about everything else. So it's kind of like a very active area of research to learn how to, in this case, represent how to make the generator represent the whole support of the data. And there's this last question, which is like more of a political discussion, which becomes how do you objectively measure the quality of a generated sample, and how do you measure it? There are empirical recommendations for all this. People have been like tinkering with GANs so much that they have come up with a bunch of recommendations that uh, which are like the use of certain types of layers in the neural networks, certain type of activation functions and optimizers. But the most important things are the theoretical recommendations, and we're gonna specifically focus on the second one here that suggests to use a weaker distance metric. Yeah. So let's wonder, what does the original GAN actually do? Well, it can be shown that the original GAN in its original formulation, the equation I showed you first, the minimax game, actually is trying to minimize the Jensen-Shannon divergence between the real and fake data distribution. This means that in the end, we're at least our purpose would be to just minimize the distance, the divergence between a couple of probability distributions. And just for completeness sake, I just added some review on distances and divergences between distributions. I know you guys should probably know a lot about this, but there's the total variation distance, the Kullback library distance, and we're gonna focus on both these measures, which is the Jensen-Shannon, which is a symmetrical divergence, and the Wasserstein distance. Yeah. As you can see, please, I ask you to take a closer look at the Wasserstein distance, because it just it's also called the Earth movers distance, and although it provides a very natural measure of distance between probability distributions, it numerically it poses a highly intractable problem. So that's something we're going to discuss further away, but just I wanted you guys to just study it for a little while. Why does it matter that we choose the right uh, distance between distribution, which is what we are actually doing here? We're actually trying to make the distribution as induced by our generator to be as close to the real data distribution as we want. So in that case, we need to choose the right distance for our intent. And why does it matter really? Well, the impact of the choice between uh, measures of distance actually has, well, its impact is reduced to basically the convergence of sequences of probability distributions. And uh, in this case, Wasserstein is the weakest among these, which means, in essence, that the easiest one for convergence is the Wasserstein distance. I'm gonna give you guys an example just to make it all just settle in our heads, and I'm just gonna show you two probability distributions. Let's see, be the uniform distribution in the interval 0 to 1, and let's just add two probability distributions, the red one and the blue one, separated by a parameter theta, on in which represents actually the horizontal distance between those two parallel lines. In this case, if you just toy with those distance metrics for a while, you're gonna find that actually the distances between those two distributions are these. I think we can start to see how the way we measure distance or divergence between distributions has an impact on things as important as convergence and actually gradients. If we try to just find the gradients on these uh, measures of distance, we'd find that, well, there's not a lot of gradient for callback library divergence or total variation distance. And there's there's a zero gradient for Jensen-Shannon. We can see that more easily here, right? So on the left, we can see the Wasserstein distance as measured by uh, uh, measuring the distance between those two distributions, uh, varying with theta. And on the right, we can see the Jensen-Shannon distance as calculated with the varying the parameter theta. So yeah, that's what's going on. We can see that while Jensen-Shannon distance does not provide any kind of meaningful gradient, uh, the Wasserstein distance provides a constant linear gradient. And that's going to be very important to us. What can be shown, what's the real issue here is that when distributions have disjoint supports, but also their intersection is contained in a set of measures 0, uh, all of these distances are gonna just flop, are just gonna kind of fail, because they are stronger metrics than the Wasserstein distance, and thus they are not gonna be, our sequences of probability distributions are not gonna converge easily on them. So that's why we are just gonna propose how to use the Wasserstein metric to measure the distance between our two distributions and to minimize that distance in order to just better and more stably generate all that data. However, as I told you, the direct application of Wasserstein distance poses a highly optimization problem. Luckily, there's this duality that basically turns our Wasserstein distance between those probability distributions into a difference, into a supremum uh, of the difference between two expectations. At this point, the discriminator is gone, and we add a function f that is a Lipschitz function. And this is when things start getting a little bit mathematically hairy, but just bear with me for a couple more slides. Um, what's important here is that under the regularity conditions provided by our function being parameterized by a neural network, we have an assurance that actually this f that's so important to us and that we have been now looking for not only exists, but also provides a meaningful gradients for our functions. And it is also as a theoretic result that this function requires its parameters to be in a compact space in order to enforce the Lipschitz condition. And that's something that we're going to solve initially by weight clipping, which means that all its weights, we're just going to clip them on the extremes on their intervals. So now, from the initial objective function, we have found that we have now a minimax gain still, but with a difference in expectations, which is kind of like an improvement. And in fact, um, besides the clipping determined by the hyperparameter C, people report several improvements, which are improved stability. We lessen the mode collapse, and now the discriminator's loss is actually correlated with image quality. But the job's not complete. Actually, weight clipping is a terrible way of enforcing compactness, and that's a direct quote from the people who wrote the Wasserstein paper. So we're just gonna add something more to it, something that's the last thing we're gonna add to our function, and we're gonna add a gradient penalty, and that's it. We have a corollary that just says that this f that we were talking about before has gradient norm almost everywhere. So this means that in order to enforce the Lipschitz condition, we only have to enforce a soft penalty on the gradient norm by sampling in between the line connecting the real and generated data. This is a mathematical result, and I can certainly provide references, but this is gonna actually help us a lot because we can now, by constraining the discriminator gradients norm, we can actually improve a lot our convergence and our stability. Our new algorithm is actually very similar from to the original one, but I hope you can notice you'll notice that the most significant part is the change in the objective function that we showed before. Whereas before we had a difference in logarithms, we now have the expected values and the gradient penalization. So yeah, that's gonna work for us, and I'm gonna show you why, well, at least some experiments as to how it improves convergence and stability. So we've come a lot. We've made a couple of years journey in just a couple of slides, and I'm gonna show you how it all comes together and just works to improve the convergence and stability of GANs. I'd like to show you how on the left we have a GAN progression, let's say we have a parabola distribution, and on the right we have on the left we have a parabola distribution uh, as being learned by a normal GAN, and on the right we have the same parabola distribution but being learned by a Wasserstein GAN with our gradient penalty. In this case, uh, we can see, well, there's not a bunch of difference really. The difference is mostly what I'm going to show you is in these blobs that we see here. Mm, do you remember the slide in which I talked to you guys about mode collapse? Well, in this slide, we can see that whereas there is no convergence on by the original GAN, we have convergence with the Wasserstein GAN with the gradient penalty on all modes of the distribution. Uh, all modes end up being represented and being sampled from if we use the or the our Wasserstein GAN with the penalized gradient. And not only that, but whereas also in these concentric circles, we can see that the original GAN can never, and I tried it like for 50 times, like the original GAN never could converge to the original distribution. The Wasserstein GAN actually does a good job at convergence to a hard distribution. And also here, there's a better convergence by the Wasserstein GAN with the penalized gradient. Mm. Finally, uh, we can, yeah, as we can see, like we can show like more consistent convergence in Wasserstein GAN than in the original formulation of GAN, and that just is a testament to the stability that is improved by using a more appropriate distance metric to measure distance between distributions. And well, and our study of basically the gradient and the and what's going to end up being more important than it may at first seem is the use of a Lipschitz function in our discriminator, because it provides more like smoother surfaces uh, than if we use like the original formulation or other formulations of GANs. Let's just jump into applications right away. I'm gonna show you something that I find like really cool. Uh, let's just, I'm gonna show you, there's this data set of cars, and we're just gonna try and generate some cars, because why not? So this is like our GAN progression. We're gonna fix our latent dimension in order to sample for every 50 epochs. I'm just gonna see what our neural network, which wasn't trained with a lot of computer power, can come up with. So yeah, I mean, those are definitely cars. It could be improved in several ways. Maybe the architecture could be refined, but I mean, you could certainly tell that these are cars, right? Well, these are some metrics that are used to just measure things. I'm not gonna go very deep into this. We can tell that there are many types of GANs really in the wild. That's why they call them the GAN zoo. They are they change architecture, they change objective. But for now, I'm just gonna show you guys uh, what kind of GANs we have been using in climate science to see if you've seen any one of these really. There's this very interesting technique called cycle GAN, which we can do image translation problems. So in this case, as you can see, we can just throw some, just input some image of a house, and then we just get back as an output the image of the same house but flooded. And well, this was used in this paper called "Visualizing the Consequences of Climate Change Using Cycle-Consistent Adversarial Networks," and it became very popular. It actually, I think, it went a little bit viral because people went like like looking at their own houses being flooded, or as if they were flooded, and it was just like a fun thing to just see and raise awareness on, maybe become, because it now can be a personal thing, I guess. This one blew my mind. I didn't know about its existence, but on the left we can see map images, original images, and on the right we can see uh, images of land use prediction with physics constrained conditional generative adversarial networks, which is amazing, really, because now we can forecast and produce real forecast and physically constrained forecast of uh, land use prediction in cities. So I thought that was really amazing. We also have here the irradiance data as simulated by generative adversarial networks. And later, I'm going to show you how closely these actually resemble the real data that they come from. Mm, yeah, so we've got like 6 classes here, only shown. There were like 10 originally, but generative adversarial networks are actually like pretty closely learning the distribution of these classes, and these have been used to just learn uh, about, well, data properties and generate samples to simulate well, plausible events coming from these properties, just daily irradiance in this case, but they are pretty generalizable, and actually they have been used to produce input like data to input data from um, to multivariate time series, and to augment data in all these image intensive applications, and they have been shown to learn the distributions very well. And the state of the art actually uses spectral normalization GANs, which uh, enforces the Lifshitz condition that I was talking to you guys before, but um, using spectral normalization, and that means just normalizing the eigenvectors, eigenvalues of the function of the function. And the first image to just come full circle, the image of the dog, the butterfly, the landscape, those were trained using this spectrally normalized GAN that enforces the Lipschitz constraint, which I think I showed you a little bit, just why it was important for us. Finally, I think GANs and their variants are just have a very high potential, and they are actually very applicable, and it's up to us to just learn what to do about them, because people have certainly figured out how to use them for very nefarious purposes, such as uh, well, deep fakes and just phishing people online and all that. And I do think it's our responsibility to just uh, figure out how to best use them for good and for the betterment of humanity. Any questions?
Great, thank you, Gabriel. That was wonderful. I know in this virtual environment, you don't get to hear the applause at the end, but rest assured, it's there. So if folks have questions, you can type them into the chat. You can use the raise hand function. You can just unmute yourself. Any of those work. I'll start. I had a question. Is there how much data is needed to make these models effective? I mean, is this something that's useful on large data sets only, or will it work with more constrained data sets?
It actually works on surprisingly few data samples. I'm talking about thousands, not hundreds of thousands or millions. Actually, if I remember correctly, the cars were trained with 10,000 samples. So that's not a lot. Sometimes it's hard, but you don't need that many samples. And people have been, there are actually a couple of papers working on how to train GANs effectively with very little data, like hundreds. So yeah, I mean, diversity is gonna suffer, you know, but you're still gonna get results that are good.
There are other questions?
Hey, Gabby, do you need a big machine to do the experiments, and how big is your how much memory do you need? Uh, what kind of software do you use? Just tell us a little bit of that.
Okay. Well, for all these experiments, if you're asking specifically about our experiments, the ones I showed you, those were trained on my machine, which at that time wasn't that powerful. It had like 8 gigabytes of RAM, and yeah, it wasn't that powerful. But it was because the neural networks weren't like very uh, big. No, but as they get bigger, you will certainly. Uh, oh, okay. As they get bigger, you're gonna certainly need like a big upgrade to your hardware. You're gonna need some how do you say it? Graphics cards, and you're gonna need to to up your CUDA cores, and you're gonna need to just uh, because it's actually two very big neural networks. So if a single neural network is just it requires a lot of computation. Just imagine two of them at the same time. So yeah, it might require a bunch of hardware upgrade on anyone's part, or a cluster, or some graphics card.
There's both a raised hand and a question in the chat. So I think Julie put her question in the chat first from Julie Poland. Can you describe more about what you're working on now related to this?
Okay. As of now, related to this, I don't know how much everyone here is knows about finance and how we can do it, but there's this quantity that is of real interest for many people, and mostly for regulators, called the value at risk. And this quantity is usually estimated using a Markov chain Monte Carlo and many other methods. And GANs have now become a new way to just try to estimate this distribution, and to just well, due to its actually powerful capabilities to just estimate probability distributions. So yeah, that's what related to what I'm working on. That would be the answer. Oh,
Great,
thank you.
Thank you. And Nachi, you had a question?
Thank you. It's really good one. You know, I think the first time I heard about this machine learning technique, excuse me, that's a really good one. I'm just thinking about like being a climate scientist, like how can we use this method in our problem? And one thing come in my mind, like as you're talking about replicating the data, something
Yeah,
like coming to my mind, like can we use it in our, we use like a stochastic weather generator, which
yeah,
is actually a statistical tool where we actually try to generate the synthetic data based on the real data, and it has a huge application in hydrology and crop modeling different where we need the daily data. For example, I can give you one example, like let's say we have a seasonal forecast every month, which is the average value of next 3 months. To use
yeah.
this data in a hydrological model or crop model, we need to disaggregate this data in a daily sequence. So I'm just
Okay.
thinking about whether this kind of method can use for this kind of problem.
Well, certainly. As I showed you, there's people working on forecasting irradiance data using GANs and showing that they actually pretty closely learn the original data distribution. So you could, yeah, that's what they're built for, to simulate and generate samples from data distributions. And the more you train them, the better the samples are going to be. So yeah, I'm sure that can be done, and not only in a single variable, but multivariate case as well. And they are pretty good at capturing relationships uh, in high dimensional data, at least so far as they have been shown to do.
That's great. So actually, it's provoked me the another question. Like for that, like what is the real gain, or like like for example, as you know, like all those kind of things we can using just a probability distribution. We can just do the random number generation from the probability distribution. So what is the real gain? I'm not talking about the computational gain. I'm talking about as application of this method. What's the real gain of
Yeah.
using that method?
Okay, what's the real gain? Uh, I could talk to you like, for example, when we calculate value at risk, they are way faster once they're trained. Actually, when you do sampling, rejection sampling, give sampling, sometimes it takes a while before we can come up with with a plausible sample. And in this case, if it's a correctly trained neural network, we can generate anything we want on demand. Um, Besides, we don't need to specify any parameters. As you know, neural networks are a universal function approximator. So uh, these these actually don't require any model presuppositions. So they, as long as we get a bunch of power, uh, we can approximate our distributions as really close as possible. I don't know your models in detail, so I couldn't tell you why it would be advantageous to use these over those, but these are the ones I can come up with right now. Besides, they use the power and the techniques of linear dependence and spatial dependence developed for neural network, which are really good at identifying self auto identifying important features, which makes our work of sampling and make our work like easier. Uh, and yeah, that's what I said. If our purpose is to just generate samples.
Okay, thank you.
Yeah.
Thanks.
Oh, thank you.
Are there other questions?
Yeah, so I've got, this is along the line of Nachi's question. And this is trying to understand the strengths and weaknesses of these kinds of approaches versus some of the other approaches we may have in our back pockets. And so you know, if I understand right, there's many situations where you might not get convergence, or you may need a lot of very strong assumptions if you were to use some of the, you know, some of the techniques that we're using already. And what this allows is, especially if there's a lot of different data, for it to sort of get the lay of the landscape, and with some strategy like you've discussed, to find a way to get convergence often when you might not be able to find something with a more how say, with another strategy. So one thing is, I think those could be some of the big advantages. I'm wondering, what are the kinds of artifacts or overfit or things to watch out for when we're using these kinds of things? If we're like using a mix of technologies, what are the kinds of things we should be wary of in terms of, like, if we make a rainfall generator, I have some instincts and I have some diagnostics to figure out when I'm working with distributions or even some non-parametric solutions, or value at risk. What are ways that I could check and see how well this is doing, what kinds of pitfalls I might have when I'm using these kinds of techniques?
Okay. Well, yeah, that's an interesting question, and it actually goes along the lines of something I was discussing of a political nature that says, how do you evaluate the quality of a generated sample? And there's several measures developed for images, actually called inception score, if that's what you would ever want. The inception score, Fréchet inception distance, which actually calculates some distance in high dimensional spaces. I could certainly show you how people are just dealing with this issue. There's also the graphs. I kind of skipped them, which showed like the losses all along our training and all the gradient norms. Those are the way we could measure if there's like a sudden drop in gradient norm. That's like a red flag. If there's like a sudden uptick on just some loss and something like that, we certainly can diagnose. And well, one of the other pitfalls that there's in the literature is that the overfitting, now that's it, of the discriminator. So sometimes the discriminator begins to just learn a little bit too quickly how to differentiate between real and fake, and thus it can't provide meaningful gradients. So because it's like a non-competitive two-player game, it's actually really difficult to balance the things. So maybe that's the issue of convergence, and that's what people are trying to improve actually. But it's gone like a long way. Actually, generative adversarial networks were invented in the end of 2014, and they are actually pretty stable now.
All right, thanks.
Yeah. No, thank you.
Great. We're getting to the top of the hour, and we want to respect people may need a few minutes before dashing off to the next meeting. So
I want to.
Oh, go ahead.
I want to just thank everyone who came, and Hugo and Angel and Weston and HR. Thank you guys for everything. I couldn't have ever imagined that I was like 2 degrees of separation away from giving a talk in the seminar here. So thank you all. And thanks for coming.
Thank you for the interesting seminar. Let's all thank Gabriel again. And if you're interested in the recording, you can access it. Or if you'd like to get in touch with him, you should have his email. So please don't feel shy to reach out. And thank you again. It's wonderful.
Oh,
Have a good day.